let's start. Okay, so effects of forces. So let's start here. So what is a force? Let's start there. What's a force? Anyone? This is where the interactivity comes in. So, Shanique, could you give us an example of what, well, not an example, but what a force is, right? The definition. Not an example, but a definition. So, from doing physics so far, what do you think a force is?
It's like
You could go ahead. It's like a.
so for like a push or pull an object that work that is exerted on an object to cause it to move or to keep it from moving.
Okay. Right, so it's a push or pull of an object, something affecting some change in position, something that causes some general displacement on an object. Right, so it's a push or pull of an object, right? Of an object specifically that has mass, that causes it to change its velocity. Right, that's what a force is. Right? So remember from our definitions, right, of what a force is in Newton's second law, the proportionality of mass and acceleration, right? So the force on an object, right, acting on an object, right, speaks to something, right? It's some causative agent, right? Some external thing, right, that causes a body mass m, right, to change its velocity, right, its acceleration, right? So F is equal to ma, right? So really going back to that, but so that's generally what we're talking about when we're speaking about forces, right? In this section of the syllabus, we're called to speak about general forces that act on simple objects, right? So let's bring up a free body diagram first. We're not going to tackle upthrust first because I think that's kind of wild, right, for the syllabus to put that first. But let's look at a general free body diagram, right? So we have, let's see, let's talk about this box here, right, resting on a table. Alrighty? So we have this here. What are the forces that we can say are acting on this block A? Go ahead.
So someone says gravity.
Gravity. All right. So we know that we have the general force of gravity. So we have some gravity acting here, right? Well, I would say, let me just put it politically correct, I guess. Is the acceleration due to gravity? So the gravitational force, right? And this is little g, which is 9.81 meters per second squared, right? So we have that acting on the object. Let me just check the chat real quick so I don't miss anything that I didn't see that. Reaction force upwards, right? So what we're seeing here now, right? That's a lovely response, right? So if an object is resting on the table, right, this surface here, right, and gravity is pulling it down towards the table, right, having some acceleration of the mass of the object, right, literally force is equal to ma, right, of that box acting downwards, right? Remember Newton's third law, every action has an equal and opposite reaction. Therefore, we're going to have an equal and opposite reaction upwards. and that is what we call Fn, or what we call the normal force. This is a reaction force, right? So it's upwards of the object. So as gravity is pressing down, right? So pushing down on the block, right? There's an equal and opposite force, right? That is directed in the, well, obviously the opposite direction, up. Alrighty? So that's fine, right? So it shows why the box doesn't just fall through the table, or the block doesn't just fall through the table, right? Because there's an equal and opposite force there's an equal and opposite force that cancels it out, right? So it just remains there, static, right? Let's say that the force, right? Let's say that a force was applied on the block, right? That causes it to move in the positive direction, right, or the positive x direction along the positive x axis. Let's say there is an acceleration this way, right? Let's say that there's some acceleration this way. The box is accelerating in that way. It's being pushed in that way, right? We are going to have a resistive force that occurs in this direction, right? What is that force?
Friction.
Friction, F. Right? So lovely. Friction is going to be that opposite force there, right? So if the body is static, then we're gonna have static friction. If the body is already in motion or dynamic equilibrium, we're gonna have kinetic friction. Right? But I didn't see any hints in the syllabus where it asks us to differentiate between static and kinetic friction. So we're just gonna name it friction. Right? So we have friction there. Okay, so we have a resistive force there. So gravity is acting down, the resistive force is a normal force, right? If the body is accelerating in some direction, right, it will feel a resistive force in the opposite direction, which is friction. Alrighty? Let's say, for example, now that, let me move this. Let's move this and let's tackle this. Put you over here. Alrighty? So that's acceleration due to gravity there, G. Right, let's say, for example, that we have something like this. We have a block B, right? This acceleration in that direction, what would that be called? If that box A is attached to another box B by a string, there will be some pulling force acting on block A. What do we call that force?
Tension.
The tension, right? So this would be acceleration due to T, the tension. So it speaks to some force applied on the object, right? Because or resulting from a string or a cord or a rope attached to said object, right? So there we have the tension. Okay, so it would be there. So here tension would be in the positive direction. Gravity would be in the negative y direction. The normal force would be in the positive y direction, and the friction F will be in the negative x direction. Right? What if we were supposed to now investigate what's happening to block B? Right? Block B has some force, gravity, in this direction, right? But it has a resistive force that is opposite to gravity heading up here, which is also the tension here, right? So I have some stuff like that. One thing that we need to note when we're talking about gravity of this object, we must also note that the object itself has some mass, right? So the gravity is causing the downward force, but the downward force isn't gravity itself, right? So let's have a look at this. Well, the downward force is resulting from gravity, right? And the mass of the box, or the blocks that we're looking at here. So really and truly what's happening here, right, is gravity times the mass of the box itself, which is the weight of the box, right? So really and truly these downward arrows are actually the weight of the objects, right? Mass times acceleration due to gravity is equal to the weight. Is that clear? Any questions? All right, give me one moment before I move on. Okay, I'm back in the room. All right, so hold on, where's my pen? Oh, there it is, right? So we're just looking at the forces, right? So when we speak about these different types of forces, right, or a force acting on an object, it is perfect, or it is, let's see, preferred rather, that you have a free body diagram. So the free body diagram is just showing a vague outline of the object, right? And arrows showing the forces and in what direction these forces are acting on said object, right? So from there now we can move swiftly into speaking about the concepts that the syllabus asks us for. Alrighty, give me 1 second. Let me just configure this thing so I can see properly, see everything that I'm talking about properly. Alrighty, so we're looking at that. So the syllabus calls us to a specific type of force. So let's look at this. Alright, this is objective 4.1. Yes, I kind of take time to start memorizing the syllabus. Alright, so objective 4.1 this. Alrighty. So let's say that we have some fluid surface, right? Let me do this properly. Let's say that we have some fluid surface here. All right. If we were to submerge an object, right, into this surface, right? So let's say that we have an object A. Some of it is submerged on the surface of this liquid or this fluid, right? So we're looking at this. We know that there's going to be a force being brought downwards on the object, right? There's a force going upwards as well. So we're just looking at the vertical components of the forces at this point in time, right? So what are the forces that we can see are acting on this object submerged in a liquid? What can we say? What are the forces acting on this object? Let's look at the forces real quick. Right, so we have an object A, right? Some part of object A is submerged. Let's call this height H, right? And its base is here at the bottom of the object here, B. Right? We're gonna have a force that's acting on the sides of the object from the liquid as molecules bombard the object, right? We're also going to have some force acting upwards on this object. Ready? So what could we say these forces are? Let me just check the chat in case persons are typing. Already, let me just check it. So upthrust, right? So what we're talking about is upthrust here. Right, so we're saying that the upward force acting on a body when it is partially, in this case is partially, or wholly immersed in a fluid, right, is the upthrust, right? The upthrust originates from the pressure differences acting on the body due to the fluid level differences, right? So what are we saying? From CSEC physics, right? H rho G, right? We're looking at that kind of concept, right? When you look at the eureka cans and stuff like that, right? The further down the object is dispersed in a liquid or immersed in a liquid, right? We're going to have higher pressures on that object or on said object, right? What are we looking at here, right? What we need to get here is the volume of the liquid displaced or the volume of the fluid displaced, right? So let's look at this. Let's derive these equations, right? So how do we find, or what is the volume of this object A, right, that is under or that is immersed rather in the fluid? How could we find that, the volume? Anyone? All right, I'm not hearing anyone. Okay, repeat.
No one's talking.
Oh no. Okay. All right. All right. So let's look at it. Right. So we're looking at the concept of upthrust or the buoyant force. Right. So the main force acting upwards on this object. Right. The buoyant force. Or upthrust due to a liquid. Right. So we're looking at that. So it can be explained through the principles of pressure and fluid displacement, right? So could somebody restate Archimedes' principle? What is Archimedes' principle? Just restate it real quick so we may move on. Anyone? Remember to unmute your mic and go ahead.
Check.
Or the buoyant force on a object is equal to the amount of water displaced.
The force is equal to the amount of water displaced. That's interesting. That's an interesting take of Archimedes' principle. Anybody would like to add to that or to ameliorate anything there? Nobody? I don't have a visual on the chat right now, so Archimedes principle.
So
Go ahead.
someone said a body at rest in a fluid is acted upon by a force pushing upward called the buoyant force is equal to the weight of the fluid that the body displaces.
Okay, lovely. So that's Archimedes' principle. Let me just finish writing the expression, right? So we're saying that when a body, right? So when a body itself, an object, anything like that, right, is wholly or partially submerged in a fluid, it experiences a general upthrust. So an upthrust that we can see, right? So the upthrust, right? And what we're going to be looking at here is that it's equal to the weight of fluid displaced. Let me just write that to the weight. That is not how I present that word. Of fluid displaced. That's really and truly what it is. Alrighty. So when the body floats in a liquid, the weight of fluid displaced is equal to the weight on the body. Right? So we're looking at that. Alrighty. So from that now, what can we gain about the property of the force here, right? The pressure and upthrust relationship. We're gonna be looking at that, right? So if we look at the relationship between the pressure and the upthrust, If you're lost, just let me know. In any fluid, we know that the pressure increases with. Go ahead. Go ahead. Go ahead.
Can you go back to the diagram, please, for a quick second?
The diagram.
Okay, thank you.
Alrighty. So we're looking at the pressure, right? So let's get this done, right? So as we increase the depth, right, the pressure will increase, right? So as you get deeper, so let's say that this is the surface of a liquid, right? As we increase this depth that we can term as H, right? As we go further in the liquid, right, the pressure will increase, right? So looking at that, due to the weight of the fluid above, right? So if an object is here, right, it's experiencing some weight of the fluid above it, right? If an object is here, it's experiencing the weight of all the fluid here that is above it, right? So we're looking at that. So the further down you are in a liquid, right, you're going to experience more pressure, right? The pressure exerted on a particular depth H, that's what we're looking at, in a fluid of density rho, right? So we're going to look at that. That relationship is given by this. So the pressure is equal to rho GH, right? Something that we've seen before in CSEC, right? So this is where P is the pressure of this acting on the object, right? Rho is the density, right? So we're looking at the fluid density, right? We also have G. What's G? G would be the acceleration due to gravity. And last but not least, H is the depth. Right? So we're looking at that relationship. So when an object is immersed in a fluid, the bottom of the object, right, is at a greater depth than the top of the object, which makes sense. The difference in this depth, right, causes pressure differential. So it causes a differing in pressures, right? And it can be related to the entire upthrust force that we're talking about, right? So what I'm going to do, right, is derive the equation for upthrust. Are you guys okay with the derivation, or you want me to just state the equation? Let me know real quick. You want me to derive the equation or just state the equation for upthrust? Just state it? Interesting. Alright, the derivation is a bit interesting, to be very honest, right? But upthrust, right, really and truly, no, we're looking at that. So this is just the pressure, right? We use the pressure. We use this equation that you had in CSEC in order to get the entire pressure, or in order to get the upthrust rather, right? So upthrust, which is, you could write, some persons write FU, some persons just put upthrust, right? So the force, right? The force upthrust is equal to, what would it be equal to? It is equal to the density of the fluid rho times the acceleration due to gravity, right, times the volume, right, of the thing displaced, right? So that's what we're looking at. So the volume of the object that is immersed in the liquid. Alrighty? So that's what we're looking at there. V can be reduced to some other components that we've seen before, you know. What would V be equal to? Anyone? The volume there, what would it be equal to? Nobody? So we're looking at this, right? The volume here, V, would be equal to the cross-sectional area, A, right, times the entire displacement of the fluid, right, or H, the height, the depth. That's what I should say, right? Times the depth, H, right? So really and truly, we can rewrite this equation as F is equal to rho G A H. Alrighty? So that would be the upthrust there, right? So that's what we're looking at there, more or less. Right, so we're looking at the area of the thing immersed in the liquid. So if we were to look at a liquid and we are supposed to be placing, let's say, a cylinder, right, in the liquid itself, right, we have to look at the cross-sectional area, right, A, of the entire thing, right, and then we're going to times it by how much of it is actually submerged in said liquid, right? We're gonna times that by the gravity G that is pulling down, right, and the density of the fluid in order to find the upthrust on the object. Alrighty? So that's really and truly what the upthrust is. Are there any questions or concerns here?
So I think someone was asking if we need the derivation for the exam.
The derivation, no, you wouldn't need the derivation, all right? But the reason why I tend to do derivations is that it doesn't matter what question you get, if you have the derivation, you can do anything, right? If you know the derivation, you can do anything. Other than if you just have an equation and they ask you about something weird, you can't really like understand where it comes from, right? You just be plugging in stuff into like equations and values to get them. If they ask for something that is not explicitly stated in the equation and you only know the equation, it may be an issue. But derivations are not necessarily stated in a syllabus to know anyways. All right. Oh, I'm just seeing. All right. So the body at rest in a fluid is acted upon by the force pushing. Yes, so that's the buoyant force. It's equal to the weight of the fluid displaced. Lovely. All right. So we're looking at these things. So that's generally what's happening here for the upthrust, right? So that would be objective 4.1, right, in the syllabus. One moment real quick. Yeah, so if we're to check the syllabus, right, it's just looking at what's happening there. Upthrust due to pressure difference, which I just stated. Alrighty, so the next thing we're looking at now is objective 4.2 in the syllabus, which is the nature, right, causes and effects of said resistive forces, right, or the different types of resistive forces that we'll look at. Alrighty, so we're moving on to objective 4.2. Alrighty, so it says to explain the nature, the cause, right, and the effects of resistive forces. Alrighty, so you can begin there. Any issues or concerns before we move on? Let me just check the chat real quick. Any issues or concerns before we move on to the next objective? Drop a 1 in the chat if we're okay to move on, and if you have a question, just please let me know. Alright, so there are no issues so far. Alrighty, so let's look at this now. So the resistive forces, right? Or what do we mean by resistive forces? We looked at some a while ago. You know, friction is an example of a resistive force, right? So what are the general resistive forces that we know? We need to know them, right? So what is a resistive force? So let's look at these. The resistive forces. Right? What are they? Anyone? What would you say a resistive force is? It's in the name. Anyone at all? Wait, repeat what you said?
The normal reaction force, one of them.
Well, yes, technically. I wouldn't say that's wrong. Generally, yeah. With respect to gravity, yes. Somebody else was saying something. I would love for you guys to raise your hand if you're going to speak, to make sure that nobody, does anything wrong or speaks over anyone. I think static or electrostatics, no. Those are potential energy relationships, right? No, not necessarily. You have resistive forces that come in those like relationships or those concepts now, but we're looking at classical mechanics, Newtonian mechanics right now. Forces that act in opposite direction of a specific force. That is true. So we're looking at forces that oppose, right? So we're looking at forces that generally oppose, right? The what would you say, the movement of an object or the motion. All right, that's really and truly what it is. Generally resulting in some energy lost, right? So often heat or deformation, right? So let's write that there. Let me just put as the example just heat. Alrighty. Deformation can happen as well, but we're not gonna look at that. Just heat. Let's look at heat. Alright, so the kinetics of the thing. Alrighty, so we're looking at resistive forces. So if an object were to move, right? So let's get back on track, right? What we were saying above about the box sitting on the table, right? So the box is there sitting on its table, minding its own business, more or less, right? And it experiences some force in this direction, right? Some force here, right? We're saying that we stated before that based on the object moving along a surface, we're going to have a resistive force, friction, F, right? Let me fix that F. It's not too pretty, right? So we have some resistance F, right? The nature of friction, right, is it has to do with materials, right? It has to do with kinetics. It has to do with the microstructure of materials, right? So if we were to look really and truly on a microscopic level of what's happening right here, right? Really and truly, we have two surfaces, right, that may be jagged in some sense, right? So let's say that this is a microstructure, right, of the box here, right, and then the surface may be rough. Right? As the box try to move in this direction, right, the rubbing, right, of these different sections, right, of the box and the surface, right, will cause some amount of heat to be lost, right, due to some brushing movement, right, or some general. I'm trying to stop like saying friction, but this is really what friction is: some moving, right, or rubbing of two objects that causes heat, right, or energy to be lost in the form of heat, right. So as we move, right, we have heat loss, right, And this entire thing is what we call friction. So if we're rubbing, so for example, if you were to put your palms together and rub your hands together, right, you will start feeling energy being lost in the form of heat, right? And that's because of the two physical objects rubbing on each other, right? So we have there, so the friction, right, of the two microsurfaces, right, will cause energy to be lost, and that is the definition of what a resistive force is, right? The block is moving in one direction, right, specifically, right, and due to the block rubbing on a surface, right, there's an opposite force, right, that creates some loss of energy, right, that causes the block to, eventually come to a stop, right? So we have that there. Remember that the block will not be moving effortlessly towards infinity, right? The resistive force that is acting on this box would be friction. So therefore, energy will continue to be lost until there is not enough energy to keep the block in motion, and then the block stops, right? So for example, when you kick a football or something like that, the football won't roll forever. There will always be some contact between the ball and the surface of the ground, causing friction, energy to be lost, and the ball will eventually stop rolling, right? So we're looking at the nature of friction, right? So that's really what it is. So the resistive force, right, resulting from the movement of an object in contact with the surface, that's really what we're looking at. No, I've never actually talked about friction, so much, but sure, that's really and truly what it is. Are there any issues or concerns there? I'd like to think not, but let's see. No? Alrighty. Let's consider a next argument. That's friction, right? Let's consider a next argument now. Right? Let's consider that an object now is launched at some angle to the horizontal. Right? So we have, let's say, a ball launched at some angle to the horizontal, right? And we have that parabolic motion there. Alrighty? When the ball is at some height, right? I don't want to use max height. At some height here, right, along the entire thing. So let's look along the entire journey. It's at some height here. Let me erase that. Question, this is, everybody should be able to identify that this is most definitely projectile motion. Alright, so let's look at this. So the ball is there at some height, using the wrong ink, or the wrong color rather. Right, so some height to the horizontal, some distance from the original vertical, right? Now, as an object moves through the air, right, the particles from the air, right, so let's say it's moving through the air in this direction, right? The particles from the air, right, will be bombarding the object, right? And that creates some amount of resistive force in the opposite direction. What resistive force is this called? Or what is this called? Alright, so hold on. I'm just thinking in the chat, somebody asked for the definition of friction, right? So I'm saying friction is a resistive force that results from the movement of one object in contact with the surface of another. That's really and truly what friction is. That causes loss of energy in the form of heat. So friction is a resistive force that acts in the opposite direction to the motion of an object in contact with the surface of another object, resulting in the loss of energy in the form of heat. Alrighty? So that's what the friction thing is. But getting back here, right? So an object is moving through the air, right? And what we're seeing here for the object, so it's air resistance, right? We're looking at, right? So what we're seeing here for the object, right? So we have the object really and truly here. Give me a second. So the object is here. Right, so the object is trying to move in this direction specifically, right? But we can note that within air, right, is a fluid, right? So while it's moving, right, there will be some bombardment of small particles, right? So there will be some bombardment of the air particles, right? This bombardment all results in an opposite force, right, that we call that is due to air resistance, right? So this is generally what we call the drag of an object, right? So drag. So it's air resistance, right? So drag due to air resistance specifically, right? So air resistance will be acting on it. So resulting in some drag, right? So the air resistance causes some drag there. Alrighty. So when an object moves in a fluid, right? A fluid is all right. What's a fluid? Let me just ask that, right, to make sure that I'm not just dispersing information without actually allowing anybody to create information. What's a fluid? What real and truly is a fluid? So you guys can raise your hand and go ahead. So what's a fluid? Nobody? Already. So a fluid specifically, right, is anything that can flow. All right, let me just say that. So it's pertaining to a substance, right? So a substance that can easily change shape, right? For example, water can change shape depending on its container, all right? So it's a fluid. Air can change shape depending on its container. So air is a fluid. So a ball moving through the air is an example of an object moving through fluid, right? And due to the resistance of that fluid, because we're speaking about a ball moving through air, that resistance would be air resistance, right? And that creates a resistive force that we call drag, right? Hopefully that makes sense. It creates a resistive force that we call drag. So as an object moves through a fluid, right, it experiences a resistive force known as drag. And remember that drag arises, right, now due to the viscosity of a fluid and differential pressure between the front and rear surfaces on the object, right? So what we're saying now, right, let's say that this object is moving through some fluid, right? It's moving this way, right? So let me just represent it. Give me a second. Alrighty. So that object is moving through some fluid, right, in that direction, right? Remember that the fluid, right, the definition of a fluid, right, it's made up of these small, tiny particles that can, flow, right? So as it moves through this fluid, right, the fluid will start to move around the object or move towards the surface of the object, right, and bombard the object, right? So you're going to have fluid moving around the object there, like that, right? The full resistive force or the full drag that is caused, right, on this box, right? So this resistive force drag is dependent on the viscosity of a liquid. So the thickness of a liquid, right? The stubbornness of that liquid to flow. So the thicker the liquid, the more the drag, right? The less thick the liquid, the less the drag on an object, right? So for example, right, air is a fluid, right? Water is also a fluid, right? When you're walking generally, right, you experience some air resistance, right? It's actually more free flowing. Let's say that we're moving our hand in the air, right? So you're moving your hand or you're waving your hand in the air, right? As you move the hand, you can feel the bombardment of these particles, right? And your hand will start to slow down or experience a resistive force. That is what we call drag. So as you move the hand through the air, right, you can feel the air moving around your hand, right? Let's say if you were to move that hand now in water, right? It's harder to move freely in water than it is to move freely in air. And that's because water is more viscous of a fluid than air is, right? Water has a higher viscosity than air, right? So when we're looking at the drag, right, or the drag that an object experiences, right, as it moves through a fluid, we have to determine what is the fluid, what's the density of the fluid, what's the viscosity of the fluid, right? If it's moving through air, it will experience some air resistance that is less resistive than the drag it will be experiencing in water. Before I move on, right, are you guys understanding what I'm saying? We're just more or less going through the concepts, right? I hold on, let me see. Alrighty. So what we're saying, an object moves through a fluid, right? As we can see stated from this diagram here, right? If you're moving through a fluid, there's gonna be fluid moving around the object, there's gonna be fluid moving towards the object. So you're flowing through that. Right? So imagine you're pushing your hand through water. You can feel the water bombarding your hand or moving around the hand, right? So all of that bombardment due to the resistance of the liquid or the viscosity of the liquid, right, is going to result in some drag. Right? So as a ball moves through air, right, the air particles bombard the ball and the ball experiences some resistance due to air, right? Or I'll call it air resistance, right? And that air resistance causes a resistive force called drag. So we're looking at that. Now, the drag that an object experiences depends on what the object is moving through. If the object is moving through air, it will experience less resistance than if it's moving through something like water, right? If an object is moving through water, it will experience less resistance than, let's say, it's moving through something like honey.